Hi everybody, this is Austin Hoggett here to give you another lecture from OpenStax Intermediate Algebra. Today we're going to be talking about rational equations and how to solve them. This lecture and the previous are sort of a culmination of topics around rational expressions. We're going to be talking about how to identify the restrictions on our equation, in other words, what the answer can't be, and then we'll look at some rational expressions that just have variables in them and how to solve or rearrange an equation in those circumstances. When it comes to solving rational equations, there's a really critical component that needs to be discussed. And the idea here is that rational equations typically have some kind of variable in a denominator. Not always, but on occasion. So the expression itself may have, polynomials in the numerator and denominator, but an equation obviously is going to be some equality. And so there's a sense in which rational equations can have solutions that are not actually solutions, oddly enough. The manner in which we eliminate the complexity of a rational equation is the same in which we eliminate the complexity for equations dealing with fractions. So you can see an example here would be instances where we're asked to solve the following equation. Now, all the regular properties of equality hold true here, and so partially we could get away with not even using this technique, but it's applicable in other domains, and so that's partly why we introduce it early on. So this idea that we can clear fractions using the LCD value is what we're going to apply to our equations today. So notice that as we identify the LCD value and use it as a multiplier, we go from a complicated situation to one that's quite simple to solve. We'll find that instances sometimes of, our solution for these rational equations is still not enough. We can develop what's called extraneous solutions to rational equations. So all the algebra leads me to a conclusion that doesn't actually give me a true statement when plugged back into the original equation. So these extraneous solutions would be sort of removed from the solution set. So partly we start any rational equation solving by identifying what are the restrictions? What can my answer not be? So looking at my denominators, I would just ask the question, how could they be made to be equal to 0? Because that's the only restrictions that we have on these rational expressions. So in our case here, we would say, well, as long as x isn't equal to 0, I won't cause any division by 0. And so that's my only restriction. The next thing we need to identify is the LCD value. So how do we find the LCD value in this case? We take a look at the denominator expressions. What are the factors? So we have x, which really doesn't factor to give me anything other than, say, x times 1. 3, which doesn't really factor to give me anything other than 3 times 1. And 6, whoops, which factors to give me 2 times 3. So how do I make an LCD out of this? Well, I've got to identify anything that they have in common. For instance, the 3 here, and of course the 1s, which don't really do a whole lot for me. And then we simply multiply the other factors. So there's also a 2 and an x. So my LCD is 6x. And we use this information now to create an equivalent equation that's a lot easier to solve. Sorry for the background noise. My dog seems to have found a chew toy that's quite squeaky. So if I take and multiply everything on each side of this equation by that LCD factor, 6x, what do we get? So an easier way to write this is to look at the expression as a product for each of these terms. So 6x times everything. Recall why we chose this value in the first place. It's because it's going to divide out all of my fractions. It's going to clear everything. So the first product here, we would have x in the numerator and x in the denominator, reducing that expression just to 6. For my next term, I would have 6 divided by 3, reducing my expression to just 2. And we also have the product of the other terms here, giving me 2x. On the right-hand side, again, we have some of the factors canceling, so 6 and 6 cancel, leaving me with just 5x. So again, which question would you rather solve, the original or this nice, easy linear equation? So now we can just use our regular properties of equality to solve. We move our variables to the same side by subtraction here, leaving me with 6 equals 3x. When I divide by 3, we finally get a solution here of x is equal to 2. Since that was not part of our restrictions, we can be confident that that's the correct answer. So this process, again, starts with identifying what can the answer not be? What are my restrictions? You set all of your denominators that have some variable in them equal to 0 and solve for x or y or whatever your variable happens to be. Naming your restrictions is important because when you get to the end, you've got to then compare that to what you get for your solutions to make sure we don't have any extraneous values. Next step is to identify that LCD, which we've gone over in previous sections. Using that to clear the fractions can be tricky, but usually we're left with one of two scenarios. In this case, we were left with a nice linear equation, meaning that our x or variable term only had 1 as the exponent. We may also have some type of quadratic or a trinomial of some kind, which would be if our variable has a square term on it somewhere. And each of those types of equations have their different techniques. For linear equations, we usually use all the properties of equality. For quadratics, we might factor and use the zero product rule. So let's look at some other examples and get a sense of how this goes. Here's another instance where I'm asked to solve. And the first thing, of course, we want to start with is what can our answers not be? What are the restrictions? So there's two denominators with variables in them. In each case, we would end up with the same solution. We would say that we don't want y to be equal to 0. Now, I could use y squared shouldn't be equal to 0, but of course, y squared shouldn't be equal to 0 tells me about as much information as y shouldn't be equal to 0. And so that's really about what we end up with, is that we shouldn't get y equals 0 as a solution. So what is my LCD value? In this case, again, I've only got two denominators. Y squared factors to give me y times y. Y, of course, factors to give me 1 times y. And so the LCD is just y squared. If I take my general equation here and I multiply everything by y squared, what are we going to end up with? So we end up with y squared times 1 minus 5 over y times our LCD. And on the other side, we have negative 6 over y squared, again, times our LCD. So lots of things gonna kind of disappear. However, we are actually going to end up with a quadratic of sorts. So as we simplify now, I'm left with y squared minus 5y equals negative 6. So how do we solve? What we have to do to solve in this case is recognize that this is now a quadratic, and therefore it needs to be solved using factoring. But first we need to put it in the correct form. Since this is a quadratic, we want to put it in the form of ax squared plus bx plus c equals to 0. In other words, we need to set the equation equal to 0 in order to be able to solve with the techniques that we're familiar with. So in this case, that involves moving our constant to the left-hand side of the equation by addition. So now I have y squared minus 5y plus 6 equals to 0. So continuing, we now factor the trinomial. Using the AC method, we can discover that factors of 6 that add up to 5 would be -3 and -2. Applying the zero product rule tells me that, in this case, y minus 3 equals to 0, or y minus 2 equals to 0. With a little bit of algebra here in each case, we find our two solutions. So why do we get two solutions? Well, again, a quadratic has a square term, which signifies the number of solutions we should expect in our problem. So comparing these to our restrictions, it looks like we don't have any extraneous values. That must be our two answers. So y equals 3 and y equals 2. Let's take a look at one more example here. In this case, again, I need to start by identifying the restrictions. And the first sort of obvious expression is y squared minus 36. This is a difference of squares which would factor to give me y plus 6 and y minus 6, right? So we do not want that to be equal to 0, which means our two restrictions are actually that y can't be a negative or positive 6. So as long as we get those two values, or anything but those two values, we're good to go. And notice that y plus 6 actually gets encapsulated in that restriction as well. So moving forward, we identify now our LCD value, which happens to also be y plus 6 and y minus 6, and use it to continue the problem. So if I take that LCD and multiply it by all of my expression, we would end up with here y plus 6 times y minus 6 times the first term is equal to y plus 6, y minus 6 times the next term, 72 over y squared minus 36. And just to cheat a little bit, I'll just say 4 times the LCD. So how do we simplify here? We look for factors that cancel out, because that's ultimately what we use this multiplication process for. So for instance, the first term we would have y plus 6 and y plus 6 canceling, where we're left then with y and the binomial y minus 6 as a product. So I still have to multiply these together, but that is all that I'm left with. On the other side, y squared minus 36 actually factors to give me both of these terms, and so they cancel each other out entirely, leaving me with just the numeric value 72. And of course, my LCD was the product y squared minus 36. So it does seem as though that, despite the complexity disappearing, we're still going to end up with some type of quadratic. And it'll take a little bit of shuffling around to get it into the proper form. Similarly to last time, we want to set our equation equal to 0 and move all of our terms to one side. So by a bit of distribution here, I end up with y squared plus 6y. On the other side, similar distribution gives me 4y squared. And in this case, we get 4 times 6 is 24. 4 times 3 is 12, plus 2, so 144. So to move everything to the right-hand side of the equation, we can just subtract. And I'll kind of do these both simultaneously just to save some space. I'm left finally with something like 0 is equal to 3y squared minus 6y. And of course, we have to figure out what negative 144 plus 72 would give me. So in that case, we actually still end up with negative 72. Now, I can factor this further using the AC method. However, it does appear that there's a common factor of 3 that could be removed that would make this a lot easier. If I just try to divide everything by 3, it simply disappears, and I'm left with the following expression. We get y squared minus 2y minus 24. So we're almost finished. I'll have to finish maybe over here in the corner. So given my expression at this stage, we need to ask what are the factors of negative 24 that would add up to negative 2. And the solution using the AC method we would find is y minus 6, y plus 4. So they'll multiply to be negative 24, but add to be negative 2. And applying the zero product rule, I would say then that either y minus 6 is equal to 0 or y plus 4 is equal to 0. And in each case, when I solve, I get y equals 6 as one solution and y equals negative 4 as the other. So these are the solutions the algebra tells me I get. However, at least one of these was part of my restrictions. So this value, y equals 6, is extraneous. We don't include it as part of the solution set. So there's really only one value for which this equation gives me a true statement, and that's if I replace y with negative 4. So let's look at a couple more examples where we're asked to do this procedure on an equation that just has variables, no numbers involved. Here I'm looking at what would have been the slope equation, and they're asking me to rearrange for the variable y. So again, I'm not actually interested in the restrictions for this one, but just what is the equation going to look like if I rearrange this such that it's solved for y. In other words, it should be y equals something as opposed to m equals something. Given my expression here, I can clear the fraction by multiplying it on each side. This is similar to multiplying everything by the LCD, but there's really only one denominator involved, so it's pretty clear that we just need to clear the fraction by multiplication of x minus 3 on each side. Now, it is a binomial. I could exactly, multiply it. However, I'm going to leave it in this form. The last thing to do is to move our constants to the same side, in this case by addition. And so we're left here with the solution y is equal to m times x minus 3 plus 2. So there's no restriction here on anything except for the variables that we would actually have to plug into this expression. For instance, we may claim that a restriction on x is that it should not be equal to positive 3. That would cause division by 0. Since we weren't really interested in solving this equation for a numeric value, it may not cause us any grief. Let's look at one more example, however. This is an instance where we're asked to rearrange the equation and solve for c. So I've actually got to consider my LCD in this case. Because there's multiple denominators, we can just multiply them together to get the LCD Cm. If I take and multiply everything by that LCD value, what's it going to look like? So we get Cm times 1 over C, Cm times 1 over M, and Cm times 1. So in this case, when I go through and simplify my expressions, again, we'll note that common factors just sort of cancel each other out. We get M plus C is equal to Cm. So how do I continue from here? We're interested in solving for C, so we want that term by itself. We need to move our variable then to the other side by subtraction, and what we end up with is this weird looking expression, Cm minus C is equal to M. It's not quite done, and so what we continue with on the other side here is factoring out the common factor C. If we were to divide each of those terms by C, you can imagine removing it by undistribution, leaving me with a binomial M minus 1. So the last phase here is to divide each side by C, or excuse me, by the other factor here, my binomial, M minus 1, to get our variable all by itself. There we go. So with our binomials canceling here, we get C by itself, along with our expression on the left-hand side of the equation, M divided by M minus 1. So it takes a little bit of a rearrangement here, but following some of the similar patterns as before, we use the LCD to clear our fractions and our properties of equality to manipulate the equation.